Okay, the first reaction we learned is about the separation of compounds, separation of organic compounds, in which one of them is amine. Okay, now the second reaction is about acylation. Acylation is when you have amides, amines have a good nucleophilic nature. They can easily attack on the acid derivatives and convert into substituted amides. In this case also, the lone pair can attack here, remove this chlorine, you can convert this into an amide form. So this amide is called acetanilide. Okay. Next, bromination. Aniline, specifically, when you react with bromine, whether you react in the presence of a non-polar solvent or a polar solvent, okay, here the concentration of bromine as a plus charge is hardly available, but here this is a rich plus charge of bromine available. Even for such small concentration or even for such high concentration, in both cases you will notice that the bromination happens very rigorously, and you will see 2,4,6 tribromoaniline formation, which will be appeared as a white ppt. Okay, in case if I want to make the mono substitution done, so first thing what we need to do is acylation, remove this chlorine out, so we will get acetanilide. Okay, and acetanilide is a moderately activating group here, because of which now if you react with Br2 in CS2, in NCRT they have they have more emphasized on using acetic acid here. Okay, so I will write that only, so which is ACOH. In that case you will see bromination happening at the para position, and thereafter when you treat with NaOH and heat or hydrolysis, now this can be also done in acidic medium as well. So even in acidic medium, the amides will undergo hydrolysis to give us, amine back. So therefore you will get para bromo aniline. So this is a single substitution. Okay. Next, amines, when you react with benzoyl chloride, it is called as benzoylization. So you can see this attacking on C double bond O, releasing Cl. So you'll get a benzoyl substitution. So that's why it is called benzoylization. Next, the third reaction is about carbyl amine test. Carbyl amine test, this, in fact, I'm rushing a bit in the first reactions is because those are all repeated ones. We have discussed this multiple times. Now, this is an important test for this topic, okay, known as carbyl amine test. It is also known as isocyanide test, specifically designed for 1 degree amines, whether it is alkyl or aryl, but it should be 1 degree. This on heating, right? So this on heating with chloroform and ethanolic KOH, that means alcoholic KOH, it forms a isocyanide, which is a foul smelling vapor. This is typically a foul smelling vapors. Got it? Now let me put the overall reaction here. The overall reaction goes like this, where you have primary amine. This I would suggest all of you can write together. Primary amine, when you treat with CHCl3 with alcoholic KOH, in that case, it will convert into R, N, triple bond C plus and minus, which is isocyanide. Okay, isocyanide plus we will get this as KCl. Okay, and H2O. Okay, this is the product formation. Clear? So how do we get this reaction here? Let's see. See, mechanism wise, if we load the mechanism, CHCl3 plus OH minus, OH minus will take away H plus, convert that into CCl3 minus plus H2. CCl3 minus will not remain stable, it will form Cl minus and CCl2. CCl2, which is dichlorocarbon is an intermediate, okay? Electrophile intermediate, or simply I'll write it as electrophile, okay? So what is the next step here? Now the amine, as a good nucleophile, will try to attack on the electrophile CCl2, which is having an empty orbital like this. So this lone pair will go connect, and that will become R, NH and H with CCl2 minus and plus. So internally you will see IMPT will take place. We will notice that RNH with CHCl2 is formed. This is the other intermediate which is formed. But we still have it in a, basic solution. So this OH minus, correct, will, first let me put it this way here as a structure. How do we get CCl2? I can write it as Cl here like this with the lone pair. Now, this lone pair can further try to push the electrons because chlorine is a good leaving group. So, as the chlorine leaves here, I'll get this as NH double bond CH Cl with a plus charge plus Cl minus. And once you get that, OH minus will attack the H plus from here, and will take away that H plus, and that will generate Rn double bond CH Cl with a lone pair. Now again the lone pair will be pushed here, Cl minus will be left. So what do I get? I'll get this as Rn triple bond CH with plus charge. And finally, because you have it still in a basic medium, this OH minus will take away this H plus to get into Rn triple bond C plus and minus, which is isocyanide. Alright, or isonitrile. You can also call it as isonitrile. Now let's look into the cases that how many number of NaOH moles we have used starting from here. So first OH minus that has been used. Thereafter we used here. Okay. Thereafter we used here. And thereafter we used here. So 3 moles have been used. So if I write the overall reaction now, okay. So overall reaction includes RNH2 of 1 equivalent reacts with 1 equivalent of CHCl3 with 3 moles of alcoholic KOH to produce 1 mole of Rn triple bond C plus and minus plus 3 moles of KCl, okay, plus 3 moles of H2, right? So this is the overall reaction, everybody. Clear? So I would suggest all of you to please check it out, how the mechanism works, and if possible, once write and practice, everybody. Okay, check quickly. Right. So you can see all these examples are of 1 degree. Okay. All of these are 1 degree amines here. They all will give positive test here. Okay. Right, sorry. Next. Check out the fourth reaction here. In fact, this reaction is also like a test. Okay. So which is Hinsberg test. Well, Hinsberg test is it's kind of a reaction also. At the same time, it is mainly used to differentiate 1 degree, 2 degree, and 3 degree. See, it is used in two ways, everybody. It can differentiate 1 degree, 2 degree, 3 degree, and also helps in separation. That means if you want to separate the solution, also it is useful. Okay. So let's see how we can do that. First, the reagent for Hinsberg is used as benzene sulfonyl chloride. The alternative reagent is tosyl or toluene sulfonyl chloride. Both will be the same nature of the reaction. Check. The idea is like this. If you had a 1 degree amine and you make a tosyl chloride reaction, that is like this. Or benzyl chloride. I can use benzyl chloride or tosyl chloride. Okay, I mean benzene sulfonyl chloride or tosyl chloride. First, it will react with primary amine. Then, as you react with KOH, okay, with KOH, it will get dissolved first. Okay, I'll show you the reaction also, don't worry. After dissolution, then when you add HCl, again you will get a precipitate. So the idea is simple. During the reaction, first a solution is dissolved by adding base and again regained by adding acid. If you do this, that means it is 1 degree amine. If initially when the reaction has happened, you got a white PPT. But on adding KOH, there is no precipitate getting dissolved. Since it is not getting dissolved, there is nothing you can make when you have HCl. So it will remain as a white PPT only. If it is 3 degree amine, the solution never forms initially a PPT at all. There is no PPT forming, so there is no question of adding HCl at all. So we take this as no reaction also. That is, this is making no reaction towards tertiary amines. Okay. So first case, first a white PPT getting dissolved in KOH, again regaining the precipitate. That is 1 degree. Second case, white PPT is not getting dissolved in KOH, so there is no question of adding KCl. Third case, there is always a clear solution and no reaction happening, so no precipitate taking place. So if this happens, this is about Hinsberg test. Now, how does the reaction take place? Let's see. If it is for 1 degree, that is, if I take primary amine, 1 degree amine. Okay, just a second. Right. So if it is 1 degree amine, as you react with TSCl, the lone pair attacks on the tosyl chloride. Remove the chloride out, and you will get a white PPT here first. Right. And see this, that white PPT, when you treat with KOH, because the amides have an available hydrogen, it can be removed out. You will get a negative charge on it, negative charge and K plus. So this becomes a soluble form. So that is the reason why this salt getting dissolved. And again, when you add HCl, it will regain the same structure and becomes a white PPT. So I hope you understood the objective here, everybody. So first you make a white PPT, dissolve that in KOH, again regain that same white PPT. This is what happens in 1 degree amine. If it was for 2 degree amines, when you add tosyl chloride, then first you'll get this amide form N comma N, I mean N comma N alkyl substitution. That is a white PPT. And when you add with KOH, you will not see any change happening. Okay. So since there is no change happening here, this will be subject to second degree. 3 degree amine, probably it is forming something like this, which is always soluble and unstable, which means this will always establish an equilibrium backwards, and backside equilibrium is more. So we also consider hardly there is any reaction happening. Okay. So this is about uh, tertiary amine. Got it? I hope all of you understood this point, how 1 degree, 2 degree, 3 degree amine works and how we can separate them also. Check it. Next is the test with HNO2, nitrous acid. Mind you, nitrous acid is always made by NaNO2 and HCl. We just need to prepare at the time of reaction, which means this will become HNO2 plus NaCl. This is freshly prepared. So this is like freshly prepared here. Okay. Next, notice if we have a 1 degree amine, correct? Something like R, CH2, NH2, and we treat this with HNO2. This will undergo diazotization, which is CH2, N2 plus, and Cl minus. This is diazonium salt. Diazonium salt. It is highly unstable. It is highly unstable. And since you are keeping this in aqueous solution, we will expect this to form a carbocation. Furthermore, hydrolysis will happen and we will see N2 gas coming out. Okay, Cl minus will be separated and alcohol formation is major product. Alcohol formation is major product. So which clearly suggests that if there is an N2 gas coming across, we say it is a 1 degree amine. Okay, if N2 gas is releasing, that means it is definitely has to be 1 degree amine. Second, if it is 2 degree amine, that is R CH2, okay, NH, and then R dash. This when you react with HNO2, in that case, instead of diazonium salt formation, it will form something like this CH2, N, right, with R dash, and this gets connected as N double bond O. Okay, so it is like a nitroso group attached here, correct? And this molecule is very stable because of the resonance stabilization from nitrogen, like this. Because of this stable molecule, this is stable, and it is stable and appears a oily yellow, oily, usually it adopts mostly yellow oily coloration. So because of yellow oil color, correct, it is very distinctly observed. So therefore this is a test for 2 degree amines, and this is also called as Lieberman nitroso test. Lieberman nitroso test. If you may remember, Lieberman nitroso test is used in two cases. One is for detection of phenol. Second is a detection of 2 degree amine. In both the cases, we call it as Lieberman nitroso test only. Okay. Third one is 3 degree amine. That is, if you have R, CH2, N, R dash, and R dash, and that when you react with HNO2, R double dash, let's say. Here also, it will be highly backward step reaction where you have CH2, N, R dash, R double dash connected to N double bond O with plus charge. Okay, and Cl minus. So this will be highly in the backward direction. So unstable form, unstable and highly reversible. Therefore, we will not perform, we will say that 3 degree does not make much of a reaction here. All okay? And in case of aryl groups, now I had to mention one thing, that when I'm writing here, first case, this is specifically meant for alkyl amines only, alkyl. But here I'm writing it for aryl amines. So in case of aryl amines, the disonium formed here, which we call it as benzene disonium salt, is stable between, or it is stable when it is less than 5 degrees Celsius. Unlike you check the alkyl groups, which is highly unstable, aryl group is quite stable. Because it is stable and you have water, we require some amount of heat to finally convert that into phenol. That means the reaction type is similar. Here also you're getting alcohol, here you're getting phenol. But the benzene here is sufficiently stable. If needed, I could actually get multiple products here by reacting with some other compounds. Because you can easily isolate this benzene disonium salt. Okay. I guess the test with HNO2 is clear, everybody. All good. Everybody, please check. Right. Now, this is one standard JE question. That is, if I have to find out all the possible products that an alkyl 1 degree amine can give, alkyl 1 degree amine can give as it reacts with NaNO2 and HCl. Okay. You know that first it forms N2 plus disonium salt. It is extremely unstable because it is an alkyl, it is highly unstable. Since it is unstable, it will easily break into carbocation. Even if it is a 1 degree carbocation, still it will break. And this 1 degree carbocation get even rearranged also. So from here it can get rearranged also. Correct. Now what are all the reagents do we have? See, first reagent we have is water, H2O. So with H2O, what does it form? It can form an alcohol here, or it can form an alcohol here. Next, we have some composition of chloride also. So because of chloride, you can get this chloride here, and here we can get 2 degree chloride. Got it? And because this reaction can be performed with some heat also, so alcohols can get dehydrated. So you will get this alkene product also. I'm talking about minor products. Next, in case if you have, ether formation, that is ether formation, this alcohol can react with this alkyl chloride to convert into a three-membered ring like this, this is one. Or this OH can react with this chloride also, and this is the way you can get this product also. This is one product. The other product is the OH here and alkyl chloride here. These two can also interact to form this type of ethers also. So please check out how many total products we got here. So 1, 2, 3, 4. These two are same. So 5, 6, 7, 8. So 8 different products we can get. Remember? So you can see total of 8 different products can be made. Got it? So this has been a JE question. Acha. NO2 minus is normally not reported. In that JE question also, there was no NO2 minus that was asked. Okay? Because the amount of NO2 minus existing will be quite less, because that NO2 minus only is converting into NO plus. So you will hardly find that. So therefore, at least you should be able to report these 8 different products. Clear? Right. See the next one. What if I give you one more similar kind of question, right? So, but this time I'm only expecting alcohol products, correct? So check other example here. What if I give you something like this, methyl, and then I have NH2 here, correct? Okay, sorry, I'll put the, yeah, NH2 here, correct? And then I treat with Na, NO2, and HCl, okay? So I'm writing possible, see, possible alcohol products. What are all possible alcohol products? So what we can do? First, I'll convert this into N2 plus disonium salt, which is highly unstable. So that will convert into a positive charge here, which on methyl migration here will convert into carbocation here, correct? And that carbocation, now once you get this carbocation, from here on we can get alcohol. So one alcohol will be formed here, and before rearrangement also I can have one alcohol formation here, like this. These two are the alcohols which are formed. So wherever the positive charge is going, you need to check out those alcohols present. Got it? Likewise, suppose if at all I have a 5-membered ring like this, correct? And I have NH2 group here, and then I'm reacting that with HNO2. So again, in a similar way, what do I do? First, you know that we can make a diazonium form which is highly unstable. And from that unstable form, you convert this into a carbocation formation. So first carbocation will form here, and that carbocation will get rearranged also to this position, which will also get rearranged to this tertiary position, which will also get ring expansion, correct? So it will also get ring expansion to get this as positive, and as it connects here, so it will become methyl and ethyl, and from here again it will get ethyl substitution here, I mean ethyl migration, because between methyl and ethyl migration is observed. So can you see these are all the carbocations which are forming. So with regards to these carbocations, what are all the products we can get? Structurally, I will be able to get this alcohol, then I will be able to get this alcohol, then with respect to this, I'll be able to get this alcohol, and with regards to this, I will be able to get this alcohol, and finally, with regards to this, I will be able to get this alcohol. Okay, sorry, ethyl. So many alcohols are possible, guys. If the question is asked with respect to stereoisomers also, that means how many stereoisomers you can get. Answer is there is a chiral center here. So there are two chiral centers here, that makes it 4. There is one chiral center here, that makes it 2. And here we have two chiral centers, that again makes it 4. Here we have again two chiral centers, that makes it another 4. So many number of stereoisomers also you can get. I guess this part is clear. So how to identify total number of alcohol products. Please check out the mechanism, and if you have a doubt, you can ask me. Right. Another such type of question you can see here, where we can have CH3NH2. When you react with NaNO2 and HCl, you can get disonium, methyl disonium form, highly unstable. It can form methanol, it can form chloride. Well, very small amount of nitrate, but this is very ignorant, usually not being used, or ethers. Correct? Likewise, this is a very interesting question which has been directly asked with the percentage amount also. Okay. And this is a repeat JE advanced question, everybody. So it is an old JE advanced question. Check. What if you have an four-membered ring amine here? Okay. So in that case, this one. Okay, sit here. So first we will get this as, you know, a carbocation here, but you know that four-membered ring is highly unstable carbocation. So now the interesting part is this four-membered ring can get compressed to get into a three-membered carbocation, because three-membered carbocation is very stable. CPM carbocation, CPM, cyclopropyl methyl carbocation. But cyclopropyl methyl carbocation shows resonating structure also in this form. This is the sigma resonance or dancing resonance is what you will say. So basically all these three carbocation formations would be observed during the mechanism. Hence, from here, if you do hydrolysis, the product what you will get here is OH. And from here, as you do hydrolysis, the product which you will get is OH. And here, if you do product formation, you will get this as OH here. Done. So these three are the products that you will get. Got it? And the percentage amount, what is observed here is 47%, 48%, and 5%. So have you noticed something that between these two, there is not much of a percentage difference? Although this is a very stable carbocation, experimentally what has been noticed is that the formation of this three-membered, because of the, I guess the reason for that would be the strain, because it is still extremely strained, correct? The percentage amount of this will be not very dominant. So remember the percentage, guys, directly asked question. Okay. No, it works vice versa also. That means if the example was given the other way around, that is, if let's say example was given like this, where a three-membered ring with NH2 is given, and that when you react with NaNO2 with HCl, so first it will form a carbocation here, and that can show resonating structure, which is like this, and it can also get rearranged to expansion in this form. So again, what do we get? We'll get the similar thing. We will get alcohol here like this. We can get an alcohol here like this. Or we can get an alcohol here like this. And the percentage remains the same, everybody. So this will be eventually 48 percentage. Sorry, this will be 5 percentage. And this will be 47 percentage. Got it? So very standard JE question, everybody. Please remember with the percentages, what are the final products form. Okay. Next, check out in case if you have aniline reacting with HNO2, you'll get diazonium salt. On adding water, you'll get phenol. Diazonium salt and adding water, you'll get phenol. Correct. This is a standard question here. And in case if you have 2-degree amine also, I'm writing everything it for, you know, aryl groups now. So that is NH and some R group here. And as I treat with HNO2, the Lieberman nitroso test is also valid for aryl also. It is not just for alkyl, it is aryl also, which means this will have N double bond O and R, which is a yellow oily liquid. Similarly, if you have R and R, that is 3-degree amine. So this is 2-degree, 1-degree, and 3-degree amine with HNO2. So we will get this as N, correct? Sorry, I'll simply write it as no reaction. That's easier instead of writing no reaction. No? So this is same as alkyl or aryl. Okay. Okay. So I hope you guys got this. What are the important reactions that you need to emphasize here? Next, when it comes to uh, other reactions here, that includes, I think, before disonium. Yeah, here. Let me come to this clear directly. Then I'll explain that disonium again. Hoffman exhaustive elimination. Okay, that is in case if you have. Hey, sorry, I forgot one thing. Sorry. Yeah, in on benzene, this is aryl, right? I forgot this is aryl. Aryl 3-degree. In case of aryl 3-degree, because you have NO plus as the electrophile, now EAS will take place, everybody. Electrophilic aromatic substitution will take place, which means NR2 here and NO formation. This is the product form. Got it? Clear, everyone? Right. Next, coming to Hoffman exhaustive elimination cases. This we have done before, how the Hoffman exhaustive elimination works. I'll just brush it up quickly. In the same chapter, we did some problems also. Let me just quickly brush it up. So basically, if you have 1-degree amine, you keep on reacting with methyl iodide, which we call it as, methylation. And if you do it in excess, you will get a lot of methyl groups here. You convert into a quaternary ammonium salt. And that when you react with Ag2O and heat, it will convert into an alkene and amine. Okay. So in this case, you can see here with exhaustive methylation, nitrogen will get like this with a plus charge and I minus. And this, when you treat with Ag2O moist, silver will take away iodide, converts into precipitate, while OH minus will try to attack on the beta position. So what are all the beta positions here? This is alpha, beta, alpha, beta. So OH minus has an option to attack on both ends. So that is OH minus can take H plus from here, or it can take H plus from here. Because this is a delayed E2 mechanism, a carbanion character will be formed, which means here a carbanion, here carbanion. Since it is a 2-degree carbanion and this is a 3-degree carbanion, so 2-degree carbanion will be more observed. So that means double bond here, and then we will get N, methyl and methyl. So more than final product in such cases, you will be asked about what would be the sequence of products here. So first would be, this plus H2. This is a product form. And if this is being performed to take, methylation again, correct? So if I do methylation one more time, So we will get three methyls here with a plus charge and like this. And now there is only one beta. Since there is only one type of beta, there is no selectivity here. So with OH minus and Ag plus here. So now this time OH minus will take H plus from here and break the bond of nitrogen here. So that converts into a product like this. Double bond and double bond here. So this is the product form. Okay. And of course, NMe thrice. This is a product. Clear? This is Hoffman's exhaustive elimination. Next is about Cope's elimination. Cope's elimination is when you have 3-degree amine converted into Hoffman elimination. Okay. If you have amine this is a 3-degree amine plus H2O2 plus this is amine oxide. Okay. This amine oxide on heating, correct? You can see which is the alpha and beta. This is alpha and beta. So again, the same problem. This is a beta at 1-degree position. This is a beta at 2-degree position. So always 1-degree position, the Hoffman product is always more favorable. So that becomes OH and the product is alkene. Okay, so this is a product formation. This is Cope's elimination, everybody. Okay, next. What is Hoffman mustard oil test? Hoffman mustard oil test is specifically again designed for 1-degree amine only. This is only done for 1-degree amine. For 1-degree amine, if we treat with carbon disulfide in the presence of mercury chloride here, like this, the presence of mercury chloride, it will start becoming Rn double bond C double bond S. Okay, this is a liquid which is formed here. Now this liquid which is formed will have, the vapors of this liquid, as it starts vaporizing, it smells like mustard oil. Okay, so this plus H2S is formed. Okay, and since you are keeping this in HgCl2, eventually this will become HGS precipitate, correct, and HCl vapors. So what do I get? I'll get a black PPT over time, and smell of this liquid as it start evaporating, it will be a smell of mustard oils or mustard seeds. Got it? That's why it is called mustard oil test. Okay. Mechanism wise is simple. C double bond S double bond S R NH2. The lone pair from here will attack, open the bond here. So we shall get this as R NH C SH double bond S. Okay. And that as you react with Hg2 plus, Hg2 plus will get precipitated. It will give you R N double bond C double bond S. How do we read it? This is thio isocyanate. So this is thioisocyanate plus that HGS will form a precipitate. So this is how you get the product form. Clear? So this is Hoffman oil test. Simple one. Next, azodye formation. Let's see what is azodye formation. Azodye formation, as in here, in case if you have aniline, you know that ring is very, very active. activated ring, and that when you react with diazonium salt, okay, maintaining the pH of the solution, maintaining the pH of the solution between 4.5 to 6. In that case, you will get a coupled product here, basically an azo product here, where you'll have N double bond N with this benzene form here. So this is azo dye, and this azo dye is yellow in color. Correct. So how's the mechanism taking place here? Check out. Okay, stepwise we'll look into it. First step is when you have aniline. Aniline is a very good donor from nitrogen's end. So it will react with pH N2 plus. So directly first it reacts here. So we will get this as NH, NH here, and N N2H. Basically N2 is in this form, no? So double bond N and pH with a plus charge here. So this is what you will get. Okay. This connection is between a nitrogen and a nitrogen, correct? So this is called N-N coupling. Remember these words, okay? N-N coupling. So first, it happens to be an N-N coupling. But now, here is the interesting part. If you keep it in acidic medium only, if you keep it in acidic medium, this H plus is not lost. So because even if this H plus is lost, because you're keeping in a mild acidic condition, the H plus will keep coming back. So that's why it cannot be isolated. I mean, of course, it can be isolated. I meant to say it will always have a charge on it. H plus will be present on it. In that case, because this concentration keeps increasing, the second mole of aniline will get a chance to this time interact, this time for carbon to interact with this nitrogen. As it interacts, this bond will break. Okay. As this bond starts breaking, correct, you will get a product as, okay, NH2 here, which gets separated out, and another aniline is getting attached this time, but this time from the carbon's end. So we will get this as N double bond N pH. So this time we call it as CN coupling. So this is what we call it as CN coupling. Okay. So remember, the reason why we require an acidic medium is to enhance that in acidic medium it can attack this way from the carbons and you can get this product. Okay. Clear? Next. What if you have a similar case where you have NH2 here? If it is NH2 here and I treat with pH N2 plus, in that case you will get this at NH2, we will get this as para position. So N double bond N and pH. In case if you have similar NH2 and this time if you treat with pH N2 diazonium, I mean coupling is done here. In that case, it will attach at this position N double bond N and pH. So which is very very similar to what we have learned in alcohols, alpha naphthol and beta naphthol. Same thing. pH should be somewhere between 4 to 6. Here also pH should be somewhere between 4 to 6. Got it? So this is how it works. Okay. So this is found out to be red color. Correct. So, but the idea is the same. Sorry, NH2 here. No? Sorry. Not red color. That is for beta naphthol. It is red color. So it is NH2. Last, in case if you have, you know, uh, NH2 here, sorry, sulfur SO3 minus here, SO3 minus Na plus, a sodium salt with N2 plus here, and that is been treated with aniline here, NH2, and this will also become an diform, azodiform here, correct? Sorry, one second, I forgot the structure. Just a minute, let me remind. Yeah, sorry, Nr2 here, methyl, two methyl groups. So if you have two methyl groups here, so in that case, the attack will be from N double bond N, and this methyl would be here with N, Me, and Me with SO3 minus and Na plus. This is again a diform, correct? Which would be usually when it is in a basic medium, or sorry, mild acidic medium, it will be slightly orangish color, orange to yellow. Okay, and this is what we call it as methyl orange. This is what we call it as methyl orange. So remember the structure of methyl orange, everybody. So this is the structure of methyl orange. So this type of product formation is called as azodite test or azodite, simply azodite formation. So the next one, anilines. Okay, aniline and aniline reactions. Quick recall again. This is aniline acetanilide. Okay, benzanilide. Okay, because there is a benzene here. So this is sulfonalic acid. Sulfonalic acid. Sulfonalic acid always exists as a Zwitter ion. This is how it exists, known as the Zwitter ion or dipolar molecule. Internal acid-base reaction. Lone pair from here will take H plus, converts into a salt form. Next, if you have COOH, it is called anthranic acid. And if you have CH3, we call it as O-toluidine. So these are all the common names. Reaction. Aniline plus HCl will give you anilinium salt. And if you have methyl anilinium, then you will get with uh, acetic acid, you will get it as salt, not with HCl. Next, with AC2O, it will become acetanilide. With bromine in the presence of CS2 or water, both things we have seen it as white PPT. We learned that how to control about bromination to get only one bromine substituted. Next, we also learned that when you react with concentrated HNO3 and H2SO4, we will mainly get para, but there will be sufficient amount of meta observed. Achha, why is that observed? Check. The lone pair present on nitrogen will maintain an equilibrium with the nitrolium anilinium ion. So this is aniline and this is anilinium ion. This is anilinium ion. And anilinium ion, when you react with NO2, because it is strongly deactivating, it will only give substitution at meta position. So that's the reason why there is a sufficient amount of composition observed even at meta position. Next, sulfonation. So that is ammonium when you react with HSO4 minus here. So first it will form a salt form here, and that on heating, this will convert into an SO3, and that SO3 will be an electrophile attached here. And that's how you will get a Zwitter ion form. Okay, so what do we call it? Sulfonalic acid. Okay, sulfonalic acid. Sulfonalic acid existing in a Zwitter ion form. So it will have a high dipole moment. Okay, sometimes in the question that wording is given, high dipole. Okay, Friedel-Crafts reactions are not observed at all in the case of NH2 because of strong activation. The lone pair will take AlCl3 and completely gets strongly deactivating afterwards. Okay, so no reaction there. Next, NHMe, when you react with AlCl3 and CH3Cl, no reaction. Second degree also no reaction here. Okay, so next, had one reaction left here, so that is benzidine rearrangement. Benzidine rearrangement, that is, if you have pH, NH, NH, and pH, this is called benzidine. And this, when you react with HCl and heat, it is like the reaction gets reversed. I mean, the chain connection will get reversed. That is NH2. Now it connects through phenyl. That becomes a biphenyl kind of a ring. And then we have NH2. How is this kind of an internal transformation happening? See, if you have pH, NH, NH, and pH, that when you react with 2H plus, so it is like we'll get this as, I'll write it in the structural form. So we will have these two connections here, NH2 plus, and here also I have NH2 plus, and these two are connected through benzene rings, like this and like this. Okay. So now on heating, this bond will break to convert into double bond. That will push to make a double bond, and this pi bond will push to make a attack on this benzene ring. That will push it to double bond, and that will push into double bond here. So what are we getting here now? So we basically will get this as NH2 double bond with a benzene form here with a double bond connection with another benzene with double bond NH2 plus and plus. This is where you will have. So because you have one hydrogen here and one hydrogen here, they will be removed out on heating. Okay, probably by Cl minus which is present. It will take away this H plus. Here it will take away this H plus, and that will retain the aromaticity. So this will push here, 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 and this will push here. So as that happens, we'll get this as NH2 connected with this benzene form and other benzene and NH2. That's it. This is the product formation. Please check. This is benzidine rearrangement reaction. Next, let's see some oxidation reactions. First, if you react 1 degree amine with alkaline KMnO4, first oxidation is towards imines. Imines will get hydrolyzed and oxidized to convert into carboxylic acids. So 1 degree amine, simple, alkaline KMnO4, you will get carboxylic acid. If it is 1 degree amine, but there are two here, earlier we had two alpha hydrogens. Here we have only one alpha hydrogen. In case of one alpha hydrogen, it will only convert into keto form. Okay. And if you have 3 degree amine, since there is no alpha hydrogen anymore, it will only convert this NH2 into NO2. So remember that two alpha hydrogens acid, one alpha hydrogen ketone, no alpha hydrogen nitro. That is a product. Say next, if you have 2 degree amine, 2 degree amine will kind of a couple with each other and you will get this NN product. If it is 3 degree amine, simply it will become 3 degree amine oxide, which we learned it as Cope's reaction or Cope rearrangement. Cope's elimination. Next, if you have any peroxy acid, in this case I'm taking Carr's acid, H2SO5, a peroxy acid. If you take 1 degree amine here on oxidation, you'll get this as uh, oxime, and 2-degree amine also gets into an oxime. Okay, if it is 3-degree, sorry, I mean 2-degree substitutions here. Okay, if you have no alpha hydrogen, in that case it will become NO. If it is 2-degree amine, it will convert into hydroxylamine. 3-degree amine, again amine oxide. Okay, these are all from Carros acid. I mean any peroxy acid. Carros acid was an example. Next, if you have aniline on oxidation, it will give you quinone. So quinone is when you use KMNO4, K2CR207 or concentrated HNO3. Okay, as a benzidine, I have written it already. Sorry. Okay. So next, check out what are all the conversions we can make. First, from benzene, if I want to get a bromine and chlorine on the opposite direction. So first, always use, these are all NCRT reactions, everybody, NCRT in-text questions. Concentrated HNO3 plus concentrated H2SO4. You do that. First, you will perform nitration, everybody, NO2. NO2, when you react with Br2 in the presence of AlCl3 or Fe, it will give you bromination, but at which position? Meta. And thereafter, you will react with tin and HCl or iron or HCl. It will reduce this into aniline. Okay, so 3 bromo aniline. And that when you react with NaNO2 in the presence of HCl, that is diazonium salt formation, which is N2 plus and Br minus. And this N2 plus and Br minus, what you get here, right? This when you react with CuCl, okay, sorry, Cu in HCl, Cu in HCl. So that will convert this into chlorobenzene here and bromine. So this is the final product formation. Okay. So what are reactions that we need to learn here? So there are, I mean, mainly the diazonium reactions. The rest all of the reactions we know. So let me go back here and just quickly brush you up through the diazonium salt reactions here. Check out what are all the reactions from diazonium salt. Okay. Right. See, this just to recall again, we have learned this in aryl halides or, if you may recall, all of these reactions we have learned in aryl halides. Just to, remind you back what are all the reactions that happens. Diazonium salt, when you react with CuCN, okay, CuCN here, okay, basically CuCN here, or simply we can write it as Cux in HX, okay, Cux in HX, both would be giving the same reactions here. So basically here you'll get this as cyanide, or here you'll get this as X. That X could be bromine, chlorine, or even cyanide also. These two reactions, or this reaction is called as Sand-Meyers reaction. Sand-Meyers reaction. While if we take copper dust, and that converts into uh, copper dust with HX, that is chlorine and bromine. In that case, again I'll get X here. So this is called Gattermann's reaction. Gattermann's reaction. Next, in case if you react with BF3 in HCl, okay, this can be written as HBF4, one of the very strong acids. In such condition, first you'll get this as N2 plus connected with, BF4 minus, some kind of a salt formation here first. Okay. Sorry, some kind of salt formation. That salt on heating is that when we will get this as fluoride here, BF3 and N2 form. So we get this as fluoro reaction. So this entire reaction set is called as Ball-Schiemann reaction. Got it? So this is called Balls, Balls, Schiemann, Ball-Schiemann reaction. Okay. See the next sequence. H3PO2. When you treat this with H3PO2 or even for that matter ethanol, in both the cases, right, you will get the product as same. First product, which is what you get here is benzene. Here also you will get this as benzene. But what is the side product? Here we'll get this as H3PO3. It gets oxidized to H3PO3. Here we'll get this as CH3CHO. This is major. Okay. It is accounted for almost in the case of uh, yeah, sorry, in the case of methanol. So if at all I write the methanol form, I'll write down here. I forgot to write the methanol form. In the case of methanol, it is slightly observed little differently here. Here mostly, just like water, OMe is a major product. Almost 100% this is a major product. It is not going to go oxidation. Next, warm water will also give you, phenol here, which is the oxidized form, right? And phenol. Next, when you react with phenol, correct, uh, it will form a azodine, OH here, and double bond N here with benzene. Likewise, here also we'll get this as NH2 here and double bond N with benzene. Okay. So both these reactions, see mechanism, what is the mechanism that is happening? Via EAS. This is via EAS. This is via SN1. Okay, ARSN1. Correct. These two are via SET mechanism. SET. Single electron transfer mechanism. Same way, this is also an SET mechanism. Single electron transfer. This is a single electron transfer. The last one is ARSN1. ARSN1, or sometimes it is in the books, it is simply written as SN1. It is one and the same. And lastly, what if I react directly with aqueous Ki? Aqueous Ki. So that will be also iodo form here like this. But this is also via ARSN1. So guys, along with the reaction product, you must know what is the type of mechanism that is happening. Okay. All of these questions have been asked in different formats. So learn in which case what is the product. Check. Other few exceptional reactions of disonium salt that includes pH, N2 plus and Cl minus. Okay. If this reacts with, you know, HASF6, very strong acid, fluorosulfuric, arsenic acid, that will also become fluorination. It will get fluorinated here. Second, in case if you react with uh, copper and KCN, that will also convert into PHCN. Or if you react with HBF4, a salt formation is observed, continued by KCN without heating, sorry, KNO2. if we react with this one, so I will get this as nitro NO2, and this is the product form. And next, if we treat with copper powder, copper powder in the presence of ethanol, so we'll get a coupling of these two, and I'll get biphenyls. This is just an extra information, guys. Okay, it's not there in GE. Usually they have never been asked. I'm just giving you an extra information. By chance, if you see these reagents, don't get confused. They are all trying to push their nucleophiles on benzene. Okay, so these are the products. Right, now let's get back to our solving once again. Right, the second conversion. The second conversion is, how do we convert benzene into this meta methyl, phenol? So how do we get this? Check. First, we treat this with concentrated HNO3. I mean, with concentrated H2SO4. This mixture will give you nitration. So first you get nitro, and then with concentrated HNO3 and concentrated H2SO4, you'll get two nitro groups here, NO2 and NO2. And if you may remember, partial reduction. So ammonium sulfide with water will give you only partial reduction. So which means only one NO2, one of the NO2 will get reduced. After partial reduction, if we treat with NaNO2 with concentrated HCl, then we'll get this as, N2 plus, N2 plus and NO2. And this with CuCN and H2O will convert into Cn with NO2. Okay. And that's when we can use SN, SNHCl, sorry, SnCl2 and HCl. What is this one? Stefan's reduction. You can perform Stefan's reduction, that will convert into an aldehyde and NO2. And once you get an aldehyde and NO2 here, correct. Now, once you get NO2 here, again, we can use Wolff-Kishner reduction, right? We can use Wolff-Kishner reduction so that the aldehydes will convert into CH3 and NO2. And now you are trying to remove that NO2 to, convert that into OH. So again, you make a disonium salt. So tin and HCl, tin and HCl. So that will give you methyl and NH2. And thereafter, disonium salt formation, HNO2. So we will get this as N2 plus. And from there, we can, because we require water or OH, so warm water. So if you react that with warm water, you'll get methyl and OH. So this is the best possible way. Please look into it carefully. What are all the reactions we perform? So my point of giving these reactions is to make sure that you understand at some point we have to do diazotization. So to do that, we usually get nitros by nitrations. Those nitrations can be always converted into disonium salts. From there, we can get any product required. Okay. So this is a very classical route. So please check. Quick, quick. Check. Next, we want to convert, the next conversion is about converting aniline into 2-bromoaniline. So let's see what we can do. Simply, we can use, you know, sulfuric acid and heat, or oleum and heat. That will give you, NH3 plus SO3 minus. What is this one? Sulfonation. Correct? Sulfonalic acid we call it. Then now you react this with Br2 in the presence of Na2CO3. So in that case, we will get this as NH2, correct? Bromine will be only present at this position and you'll get this as SO3 minus. And you know that SO3 minus will always undergo ipso substitution when you treat this with H plus and heat. Dilute H plus and heat, it will give you ipso substitution, which means SO3 will go away, hydrogen will come out. So this is another important way of conversion into products. Clear, guys? Okay. Let me put the last one here. Fourth one, from benzene, I want to convert this into, this form. That is N double bond N and N and like this one, H. This is a form I want to get. So now let's see how we can make this reaction to happen. First, I want to get nitration done. I mean, somehow we need to get nitration because there are sufficient nitrogens present on it. Okay. So we got to do that for sure. So, well, let's see what we can do. So first, I can first make a nitration here. Correct. So I will get this as concentrated HNO3, concentrated H2SO4. So, right, first you'll get NO2, right? And now what we can do, so I need to somehow get another NO2 here. So that will help a lot. So to get one more NO2 here, first what I can do here is, you can see the same reaction which I did above, I can do that. That is concentrated H2SO4. Oh, sorry, I can't do that. Oh, sorry. First I need to make reduction. SN and HCl. So SN and HCl will convert that into NH2. And that when you react with, H2SO4, right, and heat. So this will become sulfonalic acid, NH3 plus and SO3 minus. And this, and now when you treat this with, uh, yeah, concentrated HNO3, correct? Concentrated HNO3 here. So nitration will happen here. So with that, we'll get this as NH3 plus, and nitration will happen at this position, NO2 and SO3 minus. And you perform this with dilute H plus and heat. we will get this as, you know, NH2 here and NO2 here. And thereafter, so once you get this NH2 NO2 here, so that's when we can make a reduction with SN and HCl. So an HN and HCl will convert this into NH2 and NH2. And NH2 and NH2 with a diazonium salt, that is HNO2, correct, at 5 degrees Celsius, less than 5 degrees Celsius, will give you this product. How? Let me just show you that product here. That is, if you have NH2 and NH2, as you react with diazonium salt, you know that one side of the product will be N2 plus. N2 का structure कैसा है? That is N2 plus and Cl minus. And at this position we have NH2. Internally, because there is a nucleophile, this will attack here, pi bond will shift here. So that is what will convert this compound into N double bond N and NH with a bond here. By the way, that ring is also aromatic. You can see this is also lone pair pi bond pi bond. So that ring is also aromatic form. Okay. So these are some important conversions, correct? So if you may have noticed, we did a lot of questions in this amines part. So these are conversion based, and if you go back, in the starting case, we did all the GOC amine basic medium and basicity comparisons, and these are all the initial examples. You can see these are all the important questions which we learned as conversions. Correct. So a lot to learn from this topic, especially this is like an assimilation of all the topics. Got it? So please make sure you go through this topic thoroughly. Okay. Uh, 1 second.